Thank you very much, Rudy. That was one of the nicest and longest introductions I've received. As one gets older, the introductions get longer and gives you less time to speak, which is unfortunate. But I want to begin by thanking the organizers, as most of the speakers at this workshop have done, for the invitation. It's a great honor to be here. And I also want to remind everybody about what we're celebrating here. We're celebrating the 30th anniversary of the Institute for Solid-State Physics here. And I have never been to Belgrade before, or the Institute, and so it's a great honor for me to be here. In addition, we're celebrating, I suppose we should celebrate every year, the 184 years of the Serbian Academy of Sciences and Arts, whose building that we're in, this beautiful building. And for those of you who, like me, couldn't read the sign at the bottom of the stairs here, this is the translation I got from my telephone. It says that the Serbian Literary Society began the story in 1841. Various other societies joined. By the way, 1841 is about the time when all the great academic societies of Europe are being formed. And the Royal Serbian Academy went through various forms, and then in its modern form as the Academy of Arts and Sciences. I've forgotten the exact year. It doesn't seem to be there, at least according to the phone. Anyway, and I also learned a little bit by looking at Wikipedia who the, I guess I have to press this. Okay. Now I'm stuck, and it's your computer, so I can't do anything. Let me go see if I can go backwards. Here we go. It's all right now. I don't know. It was sleeping. So here are some members. You've all heard of Nikola Tesla. And I'm sure the Serbians in the room have heard of Ivo Andrić, the great novelist, and Mihailo Pupin, whom I happen to know because I worked at Columbia University for a semester, and the building is named after him, great Serbian-American inventor. And there are lots of other people who were members at various times: Mendeleev, Victor Hugo, Leo Tolstoy, Jakob Grimm, Anton Dvorak, Henry Moore, and the list goes on and on and on. It's very interesting to read. Okay, so my goal here is to talk primarily to students. So the experts on superconductivity in the audience, I apologize in advance to you, but I would really like to convince the students here of one single point, which is, although superconductivity is one of the oldest, if not, let's say one of the oldest problems in condensed matter physics, it still refreshes itself constantly. And there are constant connections with new experiments and new materials, which lead to the field raising new questions that no one ever thought of before. So in both experiment and theory, this field is rather remarkable in that sense. And it's a great place for a student to start a career. Okay, so I start by showing you some of the co-workers I've had in various projects over the years. They're divided roughly into those who passed through at one point in their life the University of Florida. That's our physics building there. And probably you recognize some of those names. Since I'm very old, they've been around the physics community for a while, and you know some of them. And on the right, they're collaborators of mine from many years of theoretical condensed matter physics research. Okay, every history of superconductivity has to start, per force, with the discovery of superconductivity in mercury at 4.2 Kelvin by Heike Kamerlingh-Onnes in the Netherlands, in Leiden, in 1911. And like I said, that's a very long time ago, particularly for students, and it seems like a very old problem. It's interesting to note what Kamerlingh-Onnes was actually looking for. He was not looking for superconductivity, of course. He was interested in a fundamental problem of the time, which was the resistivity of metals. And he developed this cryogenic technology, at least in very large part, because he wanted to understand what the resistivity of a material, I shouldn't say a metal, a material, does as you go down to zero temperature. And there were three theories available at the time. Remember, this is pre-quantum mechanics, more or less. And so there were predictions that the resistivity of a metal would be infinite. There were predictions that the resistivity of a metal would go to zero, and there were predictions that it would be finite. Okay, so basically all possibilities were on the board. It's typical of the theory community. They had all the options covered, they thought, except that Kamerlingh Onnes, found something new. He found that before it got to zero, the resistivity went to zero. Before its temperature got to zero, the resistivity went to zero. So I'm going to skip over a lot of the history between 1911 and 1957, but for the theorists, it was well known that this was a very, very obviously important problem in quantum theoretical physics, and essentially everyone that you know about worked on this problem. I recommend to you, if you haven't seen it already, a beautiful article by Jörg Schmalian in a volume entitled 50 Years of BCS, where he goes through the failures, the incredibly creative failures that were proposed by theoretical workers to explain the phenomenon of superconductivity over these 50 years. And I then go on to this quote from someone you know: "No one is brilliant enough to figure it out." This is obviously a theorist who was very frustrated, and that was Richard Feynman. And so here's a picture of some of the famous people. Bohr has already come up today. Landau, Feynman, Einstein, Heisenberg, they all worked on this problem and they all failed. Okay, so who succeeded? We'll get to that in a second. Let me remind you of these failed theories a little bit, because I think they're very interesting and instructive. So Einstein had a theory which I confess I don't really understand his idea very well, but what he said about it was supercurrents are carried through closed molecular chains where electrons undergo continuous cyclic exchanges. It always sounded to me a little bit like a sliding charge density wave, but I'm not sure if that's what he had in mind. In any case, it didn't work, and he recognized that. Here's a proposal by Landau, which is not the year, it's 1933, and he said, let's write the free energy of the system as a functional of the current, okay? And let's design a free energy which for t greater than Tc is quadratic, and for t less than Tc has these two minima. It's got a quartic term where the quadratic term changes sign, and therefore at the ground state, when the temperature is small, will be zero current we'll have a finite flowing current, okay? So he thought that superconductivity was essentially a persistent current, and that's what he was looking to describe in his theory. And the critical current went to zero at the critical temperature. It all looks a little bit familiar. Of course, it's not quite the right idea because of the theorem of Bloch a couple of months later, I think, where he proved that for a very general set of conditions, you could show that the quantum mechanical system had to have the current equal to zero in the ground state. But on the other hand, this theory of Landau was revived many years later, 4 years later, to describe the ferromagnet, right? And you just change the order parameter from J to M, and it's a very general machinery that he had thought of, and obviously took it much, much further. I want to mention before I go on the last bit of history here in that period, the Bloch's second theorem, which was that every theory of superconductivity can be disproved, which statistically still holds today, I would say, probably. Okay, what was the right answer? In 1957, these gentlemen, Bardeen, Cooper, and Schrieffer, you all know, came up with the notion of a coherent many-body pair state. They wrote down a wave function, which has an amplitude for an empty state and an amplitude for a occupied state, these two terms here. They assumed that the order parameter had S-wave symmetry, the order parameter being this anomalous average of the pair operator with some interaction, some attractive interaction that they assumed, and they knew came roughly from the electron-phonon interaction. So the picture that we have now within this BCS theory, of course, is that there's a superconducting ground state, which consists of coherent pairs. It occurs when you take a degenerate electron gas, you turn on a weak attractive interaction, and these pairs form in L equals 0, S equals 0 state. They become coherent, and you get, instead of a gas of free electrons, you get a gas of Cooper pairs. When you have an attraction, you get pairs. Why do you need pairs? The naive answer is that Bose-condensation takes place because the two electrons behave like a boson, like a molecule of bosons. And I've already skipped over the punchline here. This is the picture that you might think of naively. And it's not the right picture of a BCS superconductor. You already saw the right one. It's a picture where the actual pairs are much larger than the interparticle distance. The coherence length, which is roughly the size of the pair, involves the Fermi velocity, and this delta gap function is much greater than the interparticle spacing. That's the size of the Cooper pair. And for a simple metal, the numbers are 1,000 angstroms and 1 angstrom for a typical electronic excitation, separation, excuse me. Remember that in this wave function, it's not just pairs, but the pairs have to be coherent, just like singing in the choir. Okay. So we can make an excited state from the ground state by breaking one of these pairs into two Bogoliubov quasiparticles. Okay, they have their own independent motion, and they can recombine. But the energy it takes to break a pair turns out to be 2 delta, where delta is this anomalous average that I told you about before. And the density of states opens up very close to the actual Fermi level of the normal metal and creates the states pile up nearby. Okay, now this is a popular talk, remember, so I have to tell you about popular reasons why electrons actually decide to get together and pair, despite the fact that they have a like charge and therefore a repulsive Coulomb interaction. Well, the one that one sees occasionally is the dance analogy that people dancing on a dance floor at some point have the inclination, maybe when the music slows down, to get together and pair up. I don't like that analogy very much. It doesn't describe anything. And this is with apologies to Maria here, who is teaching a course on the physics of dance. But nevertheless, it's not my favorite analogy for superconductivity. It was one that Bob Schrieffer used when he gave popular talks. But he also mentioned another analogy, which I like a little bit better and is a little more descriptive. If anyone has ever been to a really old motel and slept with a partner on an old mattress, then you know that there is a tendency to roll together. And what you're doing in the process is two of you are polarizing the medium, suppressing the mattress between you, and therefore there's an attractive force. So that works rather well. You have to be careful what audience you tell that to. So the slightly more accurate picture is that you have an atomic lattice where the ions are positively charged. An electron comes in with some momentum. It polarizes the lattice. It's fast, and the ions react very slowly, so that excess charge builds up and it stays for a while. It's around when the second electron comes along with opposite momentum, and it can take advantage of that excess positive charge to lower its energy. And if you do a simple calculation for a electron gas with a neutralizing positive background charge, that's called the Jellium model, you find that there's a screened Coulomb part of the interaction and an electron-phonon interaction which has some dynamics associated with the dynamics of the electrons and the fast electrons and the slow ions in this picture. Now, if you notice that when omega goes to 0, that these two terms exactly cancel each other. And so you would think there's no interaction whatsoever. And all that means is that we haven't actually examined the details of the system very carefully. And if we do so, then you see that those terms are still there, roughly speaking, but they're weighted slightly differently. And so you can have a material which is a superconductor or one which is not a superconductor, depending on very small differences in details. I do want to note before I go on, because it's important for later, that the whole mechanism that I've described here depends on the electrons avoiding each other in time. They're at the same point in space, but not at the same time. So this different weighting factors, according to the details of the system, explains the fact that if you go across the periodic table, you see that some elements are superconducting and some are not. In fact, famously, the transition metals in these two columns are not superconducting at all. Some materials become superconducting under pressure. Those are the green ones. The yellow ones are superconductors at ambient pressure. Okay, so here's our question. All right, so this was more or less the state of superconductivity experiment and theory in 1961. Obviously, I've skipped over a tremendous amount. The basic problems, the objections to the theory had been more or less worked out. And Brian Pippard, who was a great scholar at Cambridge and Bristol, a great superconductor phenomenologist, went to IBM in New York and gave a speech which was called The Cat and the Cream, which became pretty famous. This is where the title of my colloquium comes from. So the quote from the talk is, "I think I might remark that in low temperature physics, the disappearance of liquid helium superconductivity and magnetoresistance from the list of major unsolved problems has left this branch of research looking pretty sick from the point of view of any young innocent who thinks he's going to break new ground." In other words, superconductivity problem is solved. Let's go on and do something else, okay? And this kind of announcement has been made from time to time. I would urge you, if you ever have the inclination to do that in your field, to think twice before announcing it in public. Because, of course, not so many years later, there were many exciting new discoveries in the superconductivity field. The first one, I'm skipping over the discovery of superfluid helium-3, which should really be in here, but I don't have time. The main one is heavy fermions in 1979. Frank Steglich in Darmstadt and his group, they discovered superconductivity in a material called cerium copper 2 silicon 2. Cerium is a rare earth element which has F electrons. This was new terrain at that time. And of course, the surprising thing was that this had been known already to be a so-called heavy electron material. The effective masses in these compounds were 100 to 1,000 times larger than the bare electron mass. And if you think about the mechanism for superconductivity that I just explained to you, I need a strong separation between the energy scales of the electrons and the ions, and that means the masses of the particles. But here, effectively, we have very heavy electrons. Why are these things superconducting? So the immediate suggestion by some people in the theory community was that the phonons in the description, the ions, had to be replaced by electronic excitations. Okay, I'm going to skip forward another 7 years to Bednorz and Müller at IBM Zurich. The possible high TC superconductivity in the barium lanthanum copper system. This is the beginning of high temperature superconductivity in the cuprates. They were awarded the Nobel Prize 1 year later. That's very unusual, but it was recognized immediately that this was a great step forward. And I want to mention that I personally came very close to this Nobel Prize, this particular Nobel Prize, me. So I think this is one of the reasons why Rudy has this great introduction for me, is that I came very close. And here is the reason. Here is the table of contents of Zeitschrift für Physik for 1987. And here's the Bednarz and Müller article, and you see right next to it is this paper that I wrote, and I think probably nobody would have even found this one if they hadn't been looking for mine. Okay, so things went on. It was an extremely rapid discovery of new materials during that period of a year or two, going all the way up to record temperature of 135 Kelvin at ambient pressure and 150 at under pressure for the mercury cuprate, the three-layer mercury material. Notice that the discovery of superconductors, these blue ones are the electron-phonon systems, was much, much slower, but MgB2 was discovered after the cuprates to be 40 Kelvin. That was quite exciting. Okay, so this was a very exciting period for everyone. Time magazine had this on the cover, the Superconductivity Revolution Wiring the Future, and it was a typical listing of all the possible applications you could do if you had a room temperature superconductor, which is what every physicist in the United States and probably around the world was telling Time magazine was going to happen. That was probably a mistake. I don't want to focus on applications here, but probably you know superconductors are good for power applications. And they can transmit currents over long distances without loss of energy. They are good in quantum circuits because they don't produce much heat. Medical technology, we already have superconducting magnets in our MRI devices, and it's very important for magnets in fusion research as well. Pardon me. So, where are we with cuprates these many years later? I don't have time to go into them in detail. There have been a couple of cuprate talks at this meeting already, and I'll give another one tomorrow. Although there are some recent new advances in wire technology in the cuprates, there have not been a great impact on technology so far, despite their high critical temperature. And that is a message for everyone looking for high TC superconductors. Here's the crystal structure. You have a layer of copper and oxygen in every single cuprate, and then different spacing layers which control how you dope the system. The phase diagram is fairly universal. There's an antiferromagnetic insulator at zero doping. As you dope chemically, you get a superconducting dome. The TC is 90 Kelvin for the bilayer systems that have received the most attention. There is a famous pseudo-gap phase where non-Fermi liquid properties are observed above TC. And eventually, what I'll talk about tomorrow is this crossover to the overdoped regime, which is still controversial. It's generally agreed that TC is too high for the electron-phonon glue to work. Calculations can be done fairly accurately now, and they show that the TC you could get from an electron-phonon interaction is way too small. So what holds the pair together? We're going to try to answer that question. But before, I'll say that there's one aspect of the system which we know pretty much for sure, and that is that the electrons do not form in S equals 0, L equals 0 pairs as the original BCS theory. Rather, they form in D-wave pairs. And that means that there's quite a bit of interesting new physics coming from the fact that the D-wave order parameter goes to 0 along the 45-degree directions in the Brillouin zone. So what's the interaction? Okay, before I get to that, a couple of more historical developments. In 2008, actually 2006, but 2008 was the big splash. Hideo Hosono in Japan discovered iron-based superconductors. That was surprising because iron was thought to be inimical to superconductivity because of its magnetic tendencies, and it was seen to be 26 Kelvin superconductor with a phase diagram. Again, a superconducting dome that was formed when you chemically doped, and there was some other feature that they noticed which turned out to be magnetism. So very influential paper, cited many, many times. And so we add these new materials to our TC versus year diagram. The critical temperature went up again very rapidly in terms of discoveries to about 55 Kelvin, and then shortly thereafter with monolayer iron selenium to about 70 Kelvin. And there it has stopped until now, I would say. These materials also have a common square lattice, not of copper and oxygen this time, but of iron and a pnictogen or a chalcogen. And then again, spacer layers to dope those planes. And they range from a few Kelvin up to 70, as I said. Iron selenium is the simplest one. It's just one iron selenium plane. Let me say a few words about gap symmetry and structure, which is something I've been particularly interested in over the years. Remember that delta, which is a function of K on the Fermi surface, is the energy gap, or the order parameter, or the pair wave function. People use them kind of interchangeably, and it's very confusing for students. So you have to sit down and see how they're all defined in terms of each other. But what I've drawn is an iron-based superconductor schematic Fermi surface. It has a hole pocket in the middle and 4 electron pockets on the outside, or actually just 2 in the Brillouin zone. And the color indicates the sign of the gap function. So if it's all green on the left, that says that on both the electron pockets and the hole pockets, the gap is plus. Whereas I could have S plus minus, just from a symmetry point of view, it's a possibility. I could have this gap with minus sign, okay? And then there's a phase change between these two inner and outer pockets. In principle, that also allows for subtle changes, which would allow for nodes on any of these pockets. But note that the first 3 examples that I show you here, they're all called A1G or S-wave states in the nomenclature. That's just because this is a tetragonal system, and if I rotate by 90 degrees or 180 degrees, this picture goes into itself. Okay, so there's no sign change under rotations. Whereas the last state listed here is a D-wave state, one of several possible D-wave states, which does change sign. Green goes into orange when I rotate by 90 degrees. Okay, let's go back a little bit to the theory of how you can get superconductivity from repulsion. A very strange idea. But in fact, it's quite old. It goes back to these gentlemen, Walter Kohn and Quinn Luttinger, in 1965, and very similar ideas from Landau and Pitaevsky in the Soviet Union at the same time. The statement, which is very clear, is that you take an electron gas model, no phonon interaction whatsoever, you have only repulsive Coulomb interactions, and that system has a ground state which is superconducting. And the idea is a new paradigm for superconductivity, which is that the electrons avoid the repulsive part of this Coulomb interaction, not in time, as I showed you before, but rather in space, because they exist in a particular kind of wave function that helps. And the idea is illustrated pretty simply here, in the sense that if you took an electron and you put it at the origin of these coordinates, then you plotted the effective potential that static charge is caused in an electron gas, you get, it's known that you get Friedel oscillations. Friedel oscillations is the electrostatic potential falls off like 1 over r cubed, but it oscillates. So there are regions of positive sign and regions of negative sign in this potential. Now, if you have a wave function which could take advantage of this, where the electron sits in an attractive region, then you can lower the energy and form a bound state. And that was Kohn and Luttinger's idea. They formalized it, of course, with the many-body calculation, where they summed up lots of screen Coulomb diagrams. And they came up with an answer which most simply expressed in the large angular momentum limit. I should mention that as I go further out here, I'm talking about larger centrifugal barriers and therefore higher angular momentum states. And so they were most interested in the high angular momentum limit. It was easier to express. And they said, okay, you get a TC, which is proportional to the Fermi energy, e to the minus some factor of order unity times L to the fourth power. That's a very big power. And if you look at helium-3, which was what they were interested in at the time, the most authoritative calculations for the potential between two helium-3 atoms said that the most attractive, the strongest channel of the potential, let me put it that way, was in the L equal 2 channel, the D wave channel. And so they plugged in L equal 2, and they got 10 to the minus 17 Kelvin. So when I was a graduate student, we used to say, oh, you've discovered Kohn-Luttinger superconductivity, and that was sort of an insult because it was something that no one obviously was ever going to be able to measure. On the other hand, it turns out that there's a more complex formula for arbitrary L, which they also worked out but didn't advertise. If you put in L equal 1, which is the correct orbital angular momentum channel for helium-3, you get about 1 millikelvin, which is pretty close to being dead accurate. Probably accidentally so, but still, it's much better. So this is the idea that you can get superconductivity from repulsion in an electron gas. So I'm just going to stop and summarize a little bit. I've got two paradigms for superconductivity. One is the electron-phonon interaction, and that is going to lead generically. I haven't really proven this, but I take my word for it. This leads rather generically to an S wave function where the order parameter does not change sign over the Fermi surface. The unconventional new paradigm that I'm talking about, where the overall interaction can be repulsive, actually leads to these order parameters where the gap or the order parameter itself changes sign. I'm going to give you an example of a very simple theory you can write down and solve on 1 or 2 pages of algebra, which is called the Birch-Schrieffer spin fluctuation theory. You take a short-range Coulomb interaction. You look at all of the diagrams in the Cooper channel. That means I look at the scattering of a k up and a minus k down particle. They do something, they interact somehow, they come out with their momentum scattered, but still zero total momentum. That's what's meant by the Cooper channel. And I sum up all these possible diagrams. I can't sum all of them, so I pick a particular subset, which are these so-called spin fluctuation diagrams, ladders and bubbles, where the red line is the screen Coulomb interaction U. You add them up, and some of you will recognize that this has a very similar structure to the Stoner theory of magnetism. In fact, if you look at the right-hand side of this equation, it looks a lot like the Stoner expression for the magnetic susceptibility of a metal with interaction U. It's expressed in terms of chi0, which is the Lindhard function, the response function of the free gas. And this on the left-hand side, it turns out to be that this is the effective attraction generated by this mechanism of spin fluctuations. It was done initially for ferromagnetic spin fluctuations, where it's an attraction. But Scalapino and Pines and others in the 90s pointed out that you could use the same mechanism on a lattice instead of with an electron gas to generate antiferromagnetic fluctuation pairing. So here's what you get if you calculate on a square lattice exactly the same thing. You get an effective interaction between electrons, which has a maximum at pi pi. And notice that it's repulsive everywhere in momentum space. Okay? Now here's the BCS gap equation. I haven't showed this to you before, but take my word for it. That's what this is. I'm going to plug in V of P minus P prime, and I'm going to assume that E is the quasi-particle energy, the energy to create a broken pair state that's positive. So supposing I try a solution where the left-hand side is positive and the right-hand side is positive, it doesn't work because I have this pesky minus sign out front. Everything on the right-hand side is positive except for this minus sign, so I can't get a solution that way. What I have to do is allow the order parameter to change sign as I go over the Fermi surface as a function of momentum. And this particular function, cosine px minus cosine py, has just the right properties that when I shift by pi pi, 0 to pi pi, I get a minus sign to take advantage of this peak. It turns out, for those of you who know cuprates, this is precisely the form of the small energy Q-dependent magnetic susceptibility measured by neutron scattering in cuprate experiments. As students still have a hard time understanding where the attraction comes from, so sometimes it's useful to plot this in real space. So you put the first electron at the center, and then you plot the attractive blue or, attractive blue or repulsive red for this particular interaction on every site of the square lattice. And you see that there are some sites which are blue, so that's where the second electron wants to sit, with the highest amplitude on the nearest neighbor. Another way to think about it is just expanding this function in a series of harmonics in k-space. And you see, even though the overall function on the left-hand side is positive, you can have contributions where, for example, this constant term in the S-wave channel is large and repulsive, and this is attractive. And still, the whole function remains positive. The principle is very easy to state, and it can be applied to any Fermi surface you like. So when these iron-based superconductors were discovered, people came along very rapidly and said, hey, I know how this spin fluctuation mechanism works. Let me do it, instead of for a cuprate Fermi surface, for this iron-based Fermi surface, which has small pockets centered on the high symmetry points of the Brillouin zone. Okay, and you see that these pockets nest rather well, and therefore there's going to be a peak in the susceptibility at this wave vector. And therefore the analogy is exactly as what I had before. You take that peak and you have to change the sign between the two pockets. And you get the so-called S plus minus state, which is thought to be characteristic of most iron-based superconductors. All right. Let me go on to more modern topics now. And I don't have time to go into any of them in detail because I want to spend a little time on one particular one. So, but this one I can't go further without mentioning because it's caused so much excitement in the community, and that is twisted moire systems and various types of bilayer systems, 2D systems, superconductivity in 2D systems. So this is the idea from Bistritsker and McDonald in 2011, that if you take two sheets of graphene and you rotate them, you get this moire pattern. And what you're doing, because graphene is a Dirac semimetal, is that you are moving the two Dirac cones slightly away from each other and giving you a Brillouin zone, which looks something like this, a very small Brillouin zone. And ultimately, if you twist at just the right angle, you can get a band structure which has a very, very narrow band, nearly separated from the other bands in the system. Now, flat bands are high density of states. High density of states is good for superconductivity. So even naively, if there were a pairing interaction around, this would be a good thing for a superconductor. What else did I want to say here? Oh, yes. So this makes twisted bilayer graphene a correlated system in the sense that although the Coulomb interactions in this material are rather weak on an absolute scale, they're rather large compared to this narrow bandwidth of the blue bands that are shown there. And that's the criterion you need for correlations in the system. And of course, this is the phase diagram that was measured by Pablo Herrero Jarillo, 2018, where you dope the system with a gate and you go from a superconductor to an insulator, correlated insulator, to another superconductor and a metal. And it all looks somewhat similar to the cuprate phase diagram, whether you dope chemically with holes to the right or electrons to the left. So I think the field will be exploring these similarities and differences for quite a while to come. And there are many other interesting 2D systems which we've heard about at this conference, which I don't have time to go through. Instead, what I want to do is focus on something which is of particular interest to me. I think if I'm a colloquium speaker, I'm allowed to talk a little bit about things that are interesting to me. And this is the experiment done by Michael Jeremitz in Mainz in 2015, where he discovered, to everybody's surprise, well, not everybody, but to many people's surprise, superconductivity at 203 Kelvin in hydrogen sulfide under high pressure. Now, this is really high pressure. This is close to a megabar of pressure, more than a megabar of pressure, in fact. And it's obtained by putting two diamond anvil cells, squeezing them together with a metallic gasket. And you see that TC gets very high and eventually made it up to 203. Okay, there's a lot of prehistory here, particularly among the theorists. So first, Eugene Wigner proposed that hydrogen, just plain molecular hydrogen, should metallize and become atomic hydrogen and then lose the electron, the valence electron, under very high pressure. That is a very old problem, and people have tried to find metallic hydrogen and eventually superconductivity in metallic hydrogen, and I think more or less failed, although there are some indications of metallicity, because the pressure needed is higher than 400 gigapascals, which is really, really at the margins right now. Neil Ashcroft, actually Ashcroft is the one who pointed out that it should superconduct. But he made an important contribution later in 2004 when he pointed out that you can also take systems with hydrogen and create potential high-temperature superconductor candidates. If you look at the transition temperature formula from, this is called the Macmillan formula or the Allen-Dines formula, the strength of the pairing is lambda. The Debye frequency, if you like, is omega log. And the strength of the pairing comes from this function, which is called alpha squared f, which is the electron-phonon spectral function. It weights the phononic frequencies with the matrix element, which is calculated for each phonon with the electronic system. And basically, the formula that he came up with, the recipe, was that you should have high omega log and an unscreened electron ion potential, and potentially chemical pre-compression of the hydrogen sublattice, meaning let the chemical pressure do some of the work for you so you don't have to go to these very high pressures. It's a little oversimplified, but that was the message that the community took away, I think. I'm going to come back to this alpha squared f a little bit later. So the discoveries in this field continued, not as rapidly as before because you need very high pressures to be able to do this. This is a material, lanthanum hydride, discovered by Russ Hemley and then confirmed by Jeremitz, where you have this cage structure. The idea is you have as much hydrogen as you can pack in. The hydrogen vibrations are very high frequencies, and that will give you a large omega log or phonon energy scale on the average. And so that went up to 250, 260 Kelvin. Now, of course, for some reason in the popular press, the holy grail is room temperature superconductivity, even though there are actually many problems associated with what you would do with a room temperature superconductor if you had one. But let's just try to understand what the temperature scales are. So I have a particular fondness for a place in Russia called Yakutsk, which is the coldest place on Earth. And the lowest temperature recorded in Yakutsk, I have to go back, is about the same temperature as the Jeremitz discovery. The average low temperature in Yakutsk in November is about the lanthanum hydride discovery. And Yeah, okay, we're going to come to the room temperature. Yeah, so the other remarkable thing about the discovery of hydrogen sulfide under pressure that I wanted to mention is that it was actually predicted by theory. Now, superconductivity theory has a very bad reputation among experimentalists for the simple reason that it's very easy to calculate the properties of a superconductor with the beautiful BCS theory, which is extremely accurate, one of the most accurate theories we have in condensed matter physics, once you know the critical temperature. But to predict the critical temperature is a very difficult problem, and you have to know the microscopic interaction, and many details go into that. This is one of the first great successes of computational superconductivity. The paper from Duan et al., where they not only predicted that the critical temperature would come out right at 100 gigapascals, but they predicted the sequence of structural transitions. Hydrogen sulfide goes in as a gas at low pressures, and then it solidifies. It goes into one structure. Then there's a structural transition to the eventual superconducting structure here. All that came out of this density functional theory plus Eli-Ashberg theory calculations. Okay, so there were many optimistic views of this hydride field, as there always are at the beginning of every superconductivity field before the hard work begins. I want to go back a little bit to show you this rather amusing plot from a paper by Warren Pickett and Michael Jeremitz. That's a nice review that they have about hydride superconductivity, where they reprinted an extrapolation, a plot made in 1970, where somebody who was rather pessimistic plotted the transition temperatures of those superconductors that had been discovered up to that time and extrapolated forward to ask when would we get a room temperature superconductor. If you do that linearly, then you're waiting for the year 2840 to get a room temperature superconductor. So we are presumably improving on that, and the improvements are described in these papers by Boeri and by another review by Warren Pickett more recently. And this is a summary of the situation in the field that was made by Brian Picard. Picard, I beg your pardon. And the purple stars here are the actual discoveries that I've described to you. Okay, those are real experimental discoveries. Every other point on the phase diagram here, or the plot of TC versus pressure, is actually a prediction. And so the theorists are a little bit ahead of the experimentalists right now, and they're making lots of predictions, and the excitement took over the field a little much. I think there were a lot of very inaccurate predictions at that time. But let me go on and talk to you about what you may have heard about, which is the melodrama that took place in the field shortly thereafter. That was initiated by someone who was searching very hard for room temperature superconductivity. And this, by the way, would be the average temperature of Yakutsk in June, just to make the comparison. This is the holy grail of the superconductivity field, according to some. And this paper appeared in Nature from Snyder et al., which is a group in Rochester, led by Ranga Diaz. And he found beautiful transitions at room temperature, basically, close enough for government work, all the way up here for zero field. That's this temperature here. That's 290 Kelvin or something like that. So that was immediately subject to some skepticism, and in particular, two gentlemen named Jorge Hirsch and Frank Marsilio published a great number of objections on the archive and to some extent in publications. They were not always polite. And the eventual consensus of the community and the University of Rochester was that Mr. Diaz had been forging some of his data. Okay, so that was a very unfortunate and tragic, if you like, circumstance in this field of someone who got a little bit ahead of himself. I want to emphasize that, one of the messages that I take away from this whole episode is that the superconductivity community has to really take note of this. The publication standards are very lax right now, and they depend on sometimes very outlandish claims. And so we need to agree as a community to tell these journals what kinds of things they should be looking for. Okay. Some of us got together and tried to, let's say, put the train back on the track a little bit by asking the very simple question, do we understand everything in the experiments which have been done so far by people other than Diaz, but do we understand that these are superconductors and not something else? And so that was, the conclusion was positive. We conclude that they do superconduct, and I can talk to anybody around about that. I think that was, I hope that was a valuable thing to do for the community. All right, I want to close in the next 2-3 minutes by talking about how you can go about looking for new superconductors. And I mentioned already the fact that the Duan et al. Paper had predicted the structural transitions correctly in the hydrogen sulfide material. And so this is a field that started about 20 years ago, or really came to fruition about 20 years ago with the increase of computational power. It's a very complex landscape when you're trying to understand how to form a particular structure. The actual kinetics of how you get from one structure to another are very complicated. There is some so-called convex hull where you plot the enthalpy versus pressure here, and there are compositions which are stable, and then there are many up here which are not. So basically you're searching for materials. You can invent stable materials if they're close to or on the convex hull, ideally. At the same time, computational methods for electron-phonon superconductivity have improved greatly. First of all, with the advent of anisotropic Migdal-Eliashberg theory, numerical Eliashberg theory from these authors, the invention of superconducting density functional theory, which is kind of a competitor to the first, by Hardy Gross in Halle. And just as a kind of a brief picture of how well they do, here are predictions from these computer programs, essentially for some simple superconductors. And the experimental temperature is the black bar, and the predictions are, the most recent predictions are the orange bars here. And so you see, it's not super accurate, but it's getting a lot closer, at least for the simple systems. So in my own group, we have several faculty at the University of Florida, including Greg Stewart, James Hamlin, Richard Hennig. You may know some of these gentlemen. And we have a great group of postdocs and students. The work I'm going to show you was done mostly by Ajinkya Hire and Jason Gibson. And the typical thing you do in this computational field, if you want to calculate TC, let's say under pressure, you first need to identify the structure. You calculate the band structure with density functional theory or some other method, but it doesn't matter. You get the phonon spectrum from frozen phonon calculations. Typically, these are relatively inexpensive computationally. Then you have to calculate the electron-phonon coupling matrix elements, and that's very costly. And then eventually you'll get this electron-phonon spectral function, which you can use to calculate TC more or less immediately. You can either estimate it from Allen-Dynes, or you can solve the Eliashberg theory to get the TC. So here's a typical alpha squared F. You have some peaks where you have prominent phonons, high phonon density of states, and high coupling constants to the electron system. Okay, this is the expensive step. So the idea is to replace this expensive step with machine learning. Okay, and reinforce it with physical knowledge of things that we know about these things that we can calculate easily, not expensively. So I can talk to anybody in private. This is just a sketch of some of our results. This is the last slide. There is, we start with a set of materials, a database of materials, crystal structures, I should say. This is the so-called Alexandria database. And we screen them down, one criterion after another. Are the phonons stable? Are the systems thermodynamically stable, i.e. close to the convex hull? Is TC that's predicted greater than 5 Kelvin? And then we plot what we get. And that there's some outliers. These are these worst cases down here that we do very poorly on. The nice thing about the prediction of alpha squared F instead of TC is that you can go back and see which phonons you missed and try to do something different. And so this is an indication that the theory is rather successful. At the end of this process, we came up with a list of 100 candidate superconductors, and we asked our friends in the laboratory to go out and synthesize some of them. And we found 2 new superconductors on this list. These are beryllium compounds, and they're not high temperature superconductors. But the goal of the project really is not to discover a high temperature electron phonon superconductor at ambient pressure, but rather to find a new superconductor which might be 30 Kelvin or 35 Kelvin, because that would immediately have, provided it's 3-dimensional, enormous technological implications for magnet technology and things like that. So that's pretty much it. What I've tried to tell you is that there are 2 paradigms for superconductivity. The conventional one, where you have to avoid the Coulomb interaction by retardation in time. The unconventional one, where you have higher angular momentum states, so you avoid it in space. There seem to be several unconventional superconductors, maybe linked by some kind of common thread. It just depends on what Fermi surface you have. I showed you superconductivity and twisted bilayer graphene. I told you a little bit about superconductivity under pressure in hydrides. And I want to leave you with the message that superconductivity is still exciting, still a field to go into as a student, and it constantly renews itself. Thank you very much.
Thank you, Professor. We were generous about time, so now we will have opportunity only for 1 or 2 questions from the audience. Okay.
Thank you for a very nice overview. So you demonstrated some very nice successes of theory and how superconductivity was predicted, right? The non-successful predictions, of course, are fading. So it's more a sociological question. How many failed predictions are there?
There's a huge number of failed predictions. But of those, I don't have a percentage. It's a good question. I don't have the statistics. But what I can tell you is, and the point I was trying to make, is if you look at all those failed predictions that I showed you, they may not all be failed, by the way. It just means that people haven't looked for it yet. But many of them probably are failed predictions. I mean that the quality of the calculations were very poor, in my humble opinion, okay? Meaning they sometimes did not check for thermodynamic stability. And that's ridiculous. You create a crystal structure and then you know it's not going to form because you haven't checked to see whether it's actually stable. I mean, density functional theory itself has errors, but at least you need to know that according to density functional theory, it's stable. And there are many other things like that, very, very low for technical people, the low resolution K-grids that were used in the calculations, those kinds of things. So accuracy goes out the window.
Okay, so it's like, take care of these parts, you think that it's actually kind of optimistic?
I'm pretty optimistic about that part, yeah. I mean, the important thing is, are there new crystal structures out there that we haven't found yet? Can we predict new crystal structures that have really essentially new physics in them? And I think there are very few examples of that right now, but I'm hopeful.
Okay.
So Peter, how can machine learning help in discovering high superconductors? Because for me, machine learning is a filter to filter the existing data rates.
Lazo, when you say high TC, you mean room temperature?
Yes.
Okay. There have been some proposals. I'll mention one of the early ones from Valentin Stanev, who used very simple neural network, I think it was random forest, took a database of many, many superconductors, focused only on the composition, namely which elements were present and how many, and tried to have the machine learn what TC was. It didn't work very well, okay? I don't think, my personal opinion here, I think this is a matter of opinion at this point. My personal opinion is that unconventional superconductivity, if that's what we're talking about, another cuprate family, is going to be very difficult to discover with machine learning, okay? Because we don't have the analog of the electron-phonon Eli-Ashberg theory, which is controlled, okay? If we did, we could do it tomorrow, but we don't, okay? Now, is there a possibility that you can get very high, close to room temperature electron-phonon superconductivity? Yes, but we've been trying now for 5 years and nobody's really getting that close. When you find a superconductor, sorry, I should make it clear. The only interesting thing is that ambient pressure, right? Because that's where the applications work. And so the closest we're able to get is we find predictions for ambient pressure superconductors that are hydrides, but the TC is reduced. So I'm a little pessimistic about finding a better hydride, frankly. But maybe there's another crystal structure with light elements. The recipe is to have light elements and covalent bonds at the Fermi surface, and I think that recipe is a real one, but it's going to take a while to achieve that, I think. And I'm not sure whether machine learning is that valuable at this point. Chris Picard would probably disagree with me, by the way. Chris Picard, yeah, right. Yes, glad. I don't know who's choosing the people, yeah.
You explained that you can predict the ordinary and heavy superconductivity with implementation theory, that we can predict the hydroids, so the BFT. But what, in your opinion, you don't understand and sound serious one?
In the whole business that I showed you?
Well, in these good topics, for example.
Well, you've given me an opportunity to get on my horse a little bit. I think that there are a lot of theories nowadays which are devoted to model systems, which are very interesting from the theoretical standpoint, which are getting further and further away from reality. So I'd like to apply Occam's razor and try to understand the materials that we know a little better. Now, the problem there is that the theory is not controlled for the unconventional systems. So I can write down a theory which will give you some possible ground states for strontium ruthenate, which is a very simple system that we should be able to understand. And yet we still can't agree on what the ground state is there. So my personal interest right now is developing a better theoretical understanding of new experimental techniques to directly probe the order parameter symmetry, or directly the pairing interaction symmetry. That's possible with Raman, as Rudy knows. Rudy knows, yes. So that's a remarkable thing for me.
Are there phenomena which your opinion say, I can't understand it?
Oh, there are many, many phenomena. I personally don't know how to. If I stood up here and said in front of a cuprate audience that I understand everything, I would be shot very quickly. No, it's really an open question. All these things are open questions, but they're fascinating questions.
Okay. Thank you very much for this lecture.
My pleasure. Thank you.